So in this session, we're going to look at some of the properties of light, and the eventual goal is going to be how much information can we extract by looking at a single beam of light, looking at the spectrum of light from some distant object. Since in astronomy, most of what we know about systems outside of our own solar system come from studying the light of those systems. So we're going to go full Sherlock Holmes and be able to see that we can extract a huge amount of information about different kinds of physical systems based on the light that they give off or reflect. We're going to learn about some of those basic properties right now. So let's just start with some of the basic properties of light. Light is an electromagnetic wave that transmits energy. Now, what we mean by an electromagnetic wave, we're going to talk about that in just a couple minutes, but suffice it for now to say, if light is acting like a wave, we can describe at least some of the properties of those waves by looking at the wavelength and the frequency. So it's described by wavelength and frequency. And this wavelength, the symbol that we're generally going to use to denote wavelength is this Greek letter lambda. So that symbol right there, this is the Greek letter lambda. And the frequency, which we're going to denote with a lowercase f. So when you think about a wave in general, the wavelength is basically how far is it from one crest to the next. If you think of water waves, then if you say one wave crest is here, the next wave crest is somewhere over here, that distance is how we define the wavelength. Whereas the frequency is how many times per second does this wave go through that kind of up and down bobbing motion. So wavelength is, again, the distance between the wave crests. Frequency is how many oscillations does that wave go through per second. And this frequency, we're generally going to measure this frequency in units of hertz. So this frequency is measured in hertz. Which is sometimes symbolized as capital H, lowercase z. And when we talk about a frequency in hertz, we're literally talking about how many cycles does it go through per second. So think about what other systems you've may have heard of before where you talk about a quantity in hertz, not the car rental company, other contexts. So you might have heard of that in terms of sound frequency, the pitch of a sound, whether it's a high frequency tone or a low frequency tone. Those pitches are measured in hertz. How many vibrations do your vocal cords go through per second? Or something like the refresh rate of a computer monitor. You might see, if you look up your monitor settings, it might have, it has a 60 hertz refresh rate or an 80 hertz refresh rate. That's how many cycles, how many refreshes of that video screen it's going through per second. Another key property of light that we're going to talk about is the speed of light. And the speed of light in a vacuum, so speed of light in a vacuum, all different kinds of light, the different wavelengths and frequencies of light that we're going to look at, all of those different wavelengths of light, if they're traveling through a vacuum, that speed of light is 3 times 10 to the 8 meters per second, or equivalently 300,000 kilometers per second. And as far as we know, for reasons that we're not going to go into too much detail in here, as far as we know, nothing can travel through space faster than this speed of light. It is the fastest possible thing in the universe. Again, we're not going to go into too many of the details of that, at least for now. But going back to this whole electromagnetic wave, there are electric and magnetic fields that can be produced by different kinds of systems. If I have some charged object, say I charge a balloon by rubbing it against my hair, Well, it gains an electric field around it. If I have a magnet, it will have a magnetic field around it. And when we talk of light being an electromagnetic wave, well, it's a set of magnetic and electric fields that are oscillating. And these variations in the electric and magnetic field will propagate through space at the speed of light. So this picture is trying to represent that. If we think of the electric field as pointing up, then pointing down, then pointing up, then pointing down, it's having this wave-like behavior. The wavelength is, again, the distance between these crests, these maximum points of this electric field. And the frequency is how many of those cycles does this wave go through per second. So if I'm watching this wave pass by, it goes up, down, and then back up. That would be one cycle, one full repetition of that motion. And these quantities that we've talked about, the wavelength, the frequency, and the speed of light, they are all related by this equation. The speed of light, let me change color for this. The speed of light equals the wavelength times the frequency. Now, there's a couple of interesting consequences to this, because we said that the speed of light, as long as they're in a vacuum, which is what we'll generally assume for this course, the speed of light is the same for all different kinds of light if it's in a vacuum. So this speed of light is staying the same. And we can think of, well, what will happen to the wavelength or frequency if I change one of those terms? For example, if I have a wave that has a very, very large wavelength. So if this wavelength is very, very large, what can we say about the frequency? Is it going to be a high frequency wave, or is it going to be a low frequency wave? Again, the question is, if we have a very, very large wavelength, what does that imply about the frequency if this speed of light is staying the same? Again, whenever I'm asking these questions, pause the video, try to work it out yourself, and then unpause it and see our discussion. Well, if the speed of light's staying the same, and I increase the wavelength, the only way that this equation will work out is if the frequency gets much, much lower. On the other hand, if I had a very, very small wavelength, a very short wavelength wave, that would imply that it has to have a very, very high frequency. So from this equation, we can say if I have a short wavelength, so short wavelength implies high frequency. And vice versa. If it's a higher frequency, then we know it's going to be a shorter wavelength. So this is one of the general properties of light. Another property of light, and again, we're not going to talk about this in too much detail. Light sometimes acts like a wave. It has certain wave properties, like this wavelength and frequency. But it also has particle-like properties. It sometimes acts like a wave, sometimes acts like a particle. Imagine you're looking at, say, the table in front of you. You know, some solid object, say, take a book or something. It seems like on the surface, it's fairly smooth. And you could have possibly imagined that if you could zoom in as much as you want to this book, that you could get as small of a piece of that book as possible. But we know that this is ultimately made up of molecules and atoms. So there is a smallest piece of the book that's possible, even though it looks fairly smooth. When you turn on a water faucet and there's water running out of the tap, it seems like it's a smooth, continuous stream of water, but we know that if we zoomed in closer and closer, it's made up of individual water molecules, H2O. In the same kind of way, if I look at a beam of light, there's light coming into my eye from the light fixtures in the room here. It seems like that's a smooth, continuous stream of light entering your eye. But if our eyes were more sensitive, we would be able to see that light is actually made up of individual little bundles of energy. light acts like a particle. And a photon, so let me write that part down. So light acts like a particle. Acts like a particle. And the photon is the smallest piece of light that you can have. So a photon is the smallest piece of light. So I could have one individual photon of light. Under normal circumstances that we're used to, when you see some light entering your eye, there are trillions of photons entering your eye every second. Just huge numbers of photons. But again, if you have very, very weak light sources, you can actually get light sources so weak that there's individual photons coming out of there, and we can detect this. Now, this equation here is how much energy do each of those photons carry? We're not going to worry about this equation. Again, there's a numerical constant in here. The main thing I want to focus on right now is this. The energy of one photon depends directly on what is the frequency of that light. The higher the frequency of that light, the larger the amount of energy that each of those photons has. Low frequency light doesn't have a lot of energy per photon. High frequency light can pack quite a bit of energy into each of those photons. So if we go back to this earlier pattern here, we said that short wavelength light has a high frequency. And now we know that the high frequency light has a high energy, so high energy per photon. So again, short wavelength light has a higher frequency, higher energy per photon. Alternatively, longer wavelength light would have a lower frequency and a lower energy per photon. So the different wavelengths of light, the different frequencies of light, they have some different properties. They have different amounts of energy per photon, and our eyes see different wavelengths of light as different colors. Those different energies of photon will react with our eyes in slightly different ways. Again, the full way that our vision works is kind of complicated and beyond what we're going to talk about in this course. But if I have blue light or green light or yellow light or red light, those are all different wavelengths of light. Okay? But that range of colors that our eyes are sensitive to is just a tiny, tiny fraction of the entire range of wavelengths that exist in nature. We're going to be looking at this thing that we call the spectrum of light. In simple cases, we can actually take some of that light and break it into its individual colors. So let's look at an example of that really quick. So one of the things that we're going to be looking at quite a bit in this course is the spectrum of light. And we can get this spectrum, when we talk about a spectrum of light, we're basically saying I'm taking a beam of light and I'm breaking up that light by wavelength to see exactly what different kinds of colors are in here, what wavelengths of light are present, how much of each type of light is present. So let's talk about that just a little bit. So I've got a material here that's called a diffraction grading. And this works very much like a prism in that it's able to break up that light into its individual colors. So for example, if I take my camera and let's say I'm looking at one of the light sources that I have here, if I hold this in front of the camera, it's able to take that light, and if I can hopefully focus decently on that, it's able to take that light and break it up into its individual colors. So if we measure exactly how much of each type of light is present here, how much of each of these colors of light is present, we can learn a ridiculous amount about the source. So I've got another example of this over here. We're going to be looking at this setup, a larger spectroscope that we have. Again, this is designed to take that light and break it up into its individual colors. And let's study a little bit about how that would work if I'm looking at a set of different colors of light. So let me get this one set up. So right now I have this spectroscope set up so it's aimed right at the white light on here. I know these colors are kind of hard to see, but it's aimed at the white light. And we see that when we break that light up, we get all of those individual colors. There's blue light in there, there's green light, there's yellow light, there's red light. All of those different kinds of light are in this spectrum. However, if I go to the red light, let me push this over a little bit and see if we can just get the red light. Well, now we see, oh, in that beam of light, there is only red light. When I move over to orange, or let's see if we can get yellow. Notice this yellow light, there's some yellow light in there. There's a little bit of green light. There's a tiny, tiny bit of red light. And again, to our eyes, when those different colors mix together, we see that as yellow. And again, as we look at different sources, so this one is kind of a turquoise. There's some green light in there. Eventually, we're getting more to the blue part of the spectrum. So now it's kind of aimed at the blue light. Basically, we can take these beams of light and get a lot more information about that light by looking at the spectrum and seeing, well, how much of each of those different wavelengths of light is present in this beam of light that we happen to be observing. And we're going to see a lot of those properties over the next couple of classes. So again, we're going to be looking at this spectrum of light and say, if we break up that light into its individual colors, we can learn a whole lot about the systems that produce that light. But the range of light that our eyes are sensitive to, what we call the visible part of the spectrum, is again just a tiny, tiny fraction of all of the different kinds of light that we see in nature. Depending on what the wavelength and what the frequency and what the photon energy of that light is, we can have all sorts of different kinds of light: gamma rays, X-rays, ultraviolet, this visible spectrum of light, infrared, and radio waves. And this full range of wavelengths that we kind of generally see in nature, they cover a ridiculously wide range, like more than 18 powers of 10 is the full range that we see show up in nature. Our eyes are barely sensitive to 1 power of 2 of that range. So again, if we're trying to study astronomy and if we're trying to study different objects by the light they give off, we don't want to limit ourselves to just looking at the visible spectrum. We want to say, how much information can I get from the ultraviolet light or the X-ray or gamma ray light or infrared or radio waves? So we're going to look at these different kinds of light. And for the spectrum of light, we often want to rank these by the different wavelengths, the different frequencies, and the different photon energies. So let's use the information that we had before and say, let's start with short wavelength light on this end, and we'll go to long wavelength light on this end. Well, if it's short wavelength, then what does that imply about the frequency of light? If we're on this section over here and it's short wavelength, what does that imply about the frequency? Well, we said if it's short wavelength, it's got to be high frequency and it's got to be high energy per photon. So over here we have high frequency and high photon energy. On the other side, we'd have low frequency. If it's a long wavelength, it's a low frequency beam of light, and it's got a lower photon energy. And we break up the electromagnetic spectrum into a bunch of different categories. Now, these categories would kind of smear together, like there's nothing all that fundamentally different about going from the shortest wavelength X-rays to the longest wavelength gamma rays. We just kind of artificially break these up into sections. But let's talk about some of these sections, because if we start at the shortest wavelength, highest frequency, highest photon energies, we're going to start with gamma rays. We've got gamma rays, and then we've got X-rays. Then we've got ultraviolet light or UV light. And then we have that range of light, that visible spectrum. So this is the visible light. And within that visible light, the shortest wavelength part of that visible light would be the blue light. And then as we move over, eventually we get some green light, get some yellow light in there, and eventually get to red light as the longest wavelength part of the spectrum. So again, the blue light would be the shortest wavelength part of the visible spectrum. Red light would be the longest wavelength part of the visible spectrum. If we go past blue, if we go to shorter wavelengths than blue and violet, well, then we get to ultraviolet. If we go to longer wavelengths than red, well, then we get into what's called the infrared. And this last section, it can be broken up further into microwaves, different kinds of radio waves, long radio waves. We're just going to list this whole section as radio waves. So these 6 different parts of the electromagnetic spectrum, gamma rays, X-rays, ultraviolet, visible light, infrared light, and radio waves, we're going to talk about some of their general properties, but I do expect students to know how are these ordered from short wavelength to long wavelength, high frequency to low frequency, sorted based on photon energy. You should be able to sort these and identify which parts of the spectrum go where. Now, before we actually do a little tour through the electromagnetic spectrum, I wanted to mention again that in a vacuum, all of these different kinds of light still travel at the same speed. Even though some of them are high energy photons and some of them are low energy photons, they all still travel at the same speed. You might ask, well, how do we know this? Well, there are some reasons on the theory side, but in terms of experimental reasons, when we look at very, very bright distant objects, things like supernovas that are exploding stars very far away, or there are these things called quasars, these active centers of certain types of galaxies, these very, very active centers that every once in a while will flare up dramatically. These objects can be hundreds of millions, and for quasars, even billions of light years away from us. They are very, very distant. And when we see these things flare up, one of the measurements that we can make is the light, as these things flare up, does all of those different kinds of light reach us at the same time? If certain types of light were moving faster than other types of light, well, and this source flared up and was giving off a lot of light suddenly, we'd expect certain wavelengths to arrive at us first. But we don't see that. To within our experimental accuracy, we haven't detected any significant difference of different kinds of light traveling through the vacuum of space. So let's do a quick little tour through the different parts of the electromagnetic spectrum. There are some numbers in here. I don't expect anyone to memorize the numbers. The things that I want to focus on instead of these numbers are just the sorting from gamma rays to radio waves. So sorted by wavelength, sorted by frequency, sorted by photon energy, and some of the general properties of when do these occur, what are they useful for, things like that. So let's start with gamma rays. This is the shortest wavelength, highest frequency, and highest photon energy. These photon energies, again, I don't expect anyone to memorize these, but just for comparison, we have these units of electron volts. You can just think of that as some unit of energy. And ordinary light, we're going to see, is around 1.5 to 3 electron volts of energy per photon. Not very much. These gamma rays are more than 1 million times more energetic per photon than visible light. So these are often given off in extremely high energy reactions, things like nuclear reactions. In fact, during the Cold War, there were a number of satellites that were placed in orbit around the Earth, looking at the Earth for gamma ray emissions. Basically, during the Cold War, there was a ban on nuclear weapons testing in the atmosphere. And since no one really trusted each other, we sent up satellites to kind of monitor this. And they started getting some hits. They started detecting some gamma rays. The difference is, what they eventually found was these gamma rays were not coming from Earth. They were actually coming from deep space, from things called gamma ray bursts. And we still don't really know a huge amount about these gamma ray bursts. We actually know what some of the sources are, but there's a variety of kinds of gamma ray bursts. So these gamma rays are extremely high energy, given off in things like nuclear reactions. If gamma rays hit you, they carry enough energy per photon to start doing things like breaking down molecules, and especially DNA molecules in your body. So they will significantly increase the risk of cancer if you get a large dose of gamma rays. X-rays, well, they're still pretty short wavelength, pretty high frequency, and still fairly high photon energy. Think, well, where are X-rays used? Well, you may have had a broken bone or gotten a dental X-ray. Those are used in medical imaging. And one of the things about X-rays is that they'll pass pretty easily through soft tissue, but certain materials like bone are a little bit better at blocking X-rays. So if I want to know if I have like a broken bone or something, I can shine X-rays on my hand and put a screen behind that, which will pick up X-rays. Those X-rays will pass through the soft tissue of my hand and hit the screen, but my bones will slightly block those X-rays. And basically, when I have the X-rays aimed at my hand and the screen behind it, my bones will cast a shadow onto that screen if we shine X-rays on that thing. So an X-ray is literally, I'm firing X-rays at my body. There's a screen behind it. If you've ever gotten a dental X-ray and had to put that thing in your mouth that's super uncomfortable, that's the screen that the X-rays are trying to hit. And your bones cast their shadow onto that device. How are X-rays given off? Well, they're given off by extremely high temperature systems, things that are at temperatures literally in the millions of degrees, or you can use high voltage sources. So in the dentist's office, they're not heating something up in there to millions of degrees. They use high voltage sources to actually generate those X-rays. And again, when we look at the sky in X-rays, this is the disk of the Milky Way galaxy looking at it in X-ray light. And there are certain systems that seem to be giving off very, very high levels of X-rays. Okay, moving on. I'm going to actually zoom in on this just a little bit more so you can see it a bit better. Ultraviolet light, still pretty short wavelength, pretty high frequency, and still at high photon energy. Think about where you've heard of ultraviolet light before. One of the main things that might come to mind are sunburns. Our sun gives off a little bit of ultraviolet light. More massive stars, younger high mass stars actually give off way more ultraviolet light than our sun does. Our sun just gives off a little bit of ultraviolet light. And again, that ultraviolet light, it still has enough energy per photon to damage skin cells. So gamma rays, X-rays, ultraviolet light, those can all damage, can have negative health consequences if you get very large doses of them. This is the Andromeda Galaxy, specifically looking at the ultraviolet part of the spectrum. Now, I said that younger short-lived high mass stars give off strong amounts of ultraviolet light. So this image, by looking at the Andromeda Galaxy in the ultraviolet part of the spectrum, will specifically highlight these areas where there has been recent star formation, where these highly energetic but very short-lived stars are still kicking around, we can see where new areas of star formation came from. Again, if we want to study astronomy, we want to use as many parts of the spectrum and study the sky in as many parts of the spectrum as possible, because different systems will give off different amounts of different kinds of light. For visible light, well, this is again the wavelengths, frequencies, and energies of light that our eyes have developed to respond to. And again, going from the shortest part of the visible spectrum, that's kind of violet and blue light, the longest wavelength part of the visible spectrum, that's going to be red. You can actually use this to help memorize the order of these different parts of the spectrum. If I go past violet, if it's earlier than violet, it's ultraviolet. If I go past red, it's infrared. And again, this is radiation that our eyes are sensitive to. Our sun emits light most strongly in this part of the spectrum, which is kind of makes sense for why our eyes have developed to respond most strongly to visible light and not other forms of light. Though it is interesting to note that other animals that have eyes that are somewhat different than ours, some animals are able to see a little bit more into the ultraviolet part of the spectrum. Other animals are able to see a little bit more into the infrared part of the spectrum. And again, this energy per photon, like I said, it's around 1.5 to 3 electron volts of energy. Compare that to the millions of electron volts of energy per photon for gamma rays. Visible light, well, it doesn't cause the same kind of damage to our cells that gamma rays have, because visible light and longer wavelengths forms of light, like infrared and radio waves, they don't pack enough punch per photon to cause the same kind of biological damage that things like gamma rays, X-rays, and ultraviolet light cause. Even though we call all of these different parts of the spectrum electromagnetic radiation, it doesn't necessarily mean that all of it is harmful to us. Going to longer wavelengths. So now we're at a little bit longer wavelength, lower frequency, and lower energy per photon. This is infrared light. Now, if you've ever seen, say, a spy movie or a movie where they're talking about having infrared goggles, well, those are designed to look at infrared light. And if I have different objects at kind of normal room temperatures, so things like body temperature, things like other objects around this room, depending on the temperature of the object, it will give off more or less infrared light. Right now, you listening to this, you are a warm-blooded mammal. Your warm body gives off, actually emits some of this infrared light. So in this image, we've got the warm-blooded person and the cold-blooded alligator. Again, the alligator's cold-bloodedness, it doesn't mean it's not giving off any infrared light. It's just giving off substantially less infrared light than the warm-blooded person. And when we look at things like lower temperature stars, failed stars, which are called brown dwarfs, certain planets, it can be very helpful to try to look at this in the infrared part of the spectrum, because those lower temperature objects give off more infrared light. The last part of the spectrum that we're going to talk about is radio waves. Now, when you hear the word radio waves, most people think of tuning into a radio station and having some sound come out of that radio. But radio waves are not sound waves. All of these different parts of the spectrum that we're talking about, they're all different kinds of light. So these radio waves are electromagnetic waves that carry information. Within that electromagnetic wave is encoded the information that your radio needs to convert that into a sound. Or for things like cell phone signals, also have an antenna built inside of them. We don't have the kind where you need to lift the antenna out anymore. It's built into the phone. And these also pick up what's in the radio portion of the spectrum. That can encode the information to send a text or send a video file, browse the internet. But these are still based on looking at light and how these radio waves can interact with that device. So for example, let's say I just pick a random radio station, let's say 91.9 FM. Well, in the FM part of the radio spectrum, that actually tells you that the frequency of this radio wave is 91.9 megahertz, 91.9 million hertz. So that radio signal that's coming in, it's oscillating 91.9 million times every second. So in this case, we actually know what the frequency of that sound is. Sorry, not the frequency of that sound, the frequency of that radio wave, which is, again, a form of light. We also know how fast light travels in a vacuum. It's 3 × 10⁸ meters per second. So we can actually use this to measure, well, what is the wavelength of this particular radio wave? If I rearrange this equation and solve for the wavelength, this Greek letter lambda, that's the speed of light divided by the frequency. So we've got 3 × 10⁸ meters per second divided by 91.6 million hertz, or million cycles per second. And if you run through the numbers on this, you'll get a wavelength of about 3.26 meters. So that would be about approximately the width of this room. So this radio signal, if you were able to freeze time and look at these oscillating electric and magnetic fields, you'd go from a peak of the electric field to a minimum, back to a peak on the other side of this room. That wavelength would be 3.26 meters for this particular kind of radio wave. So if you have a radio station that you like, or if you look upon your phone and say, well, what frequencies does my phone use? Your phone uses much higher frequencies than this, usually in the gigahertz range, or billions of hertz. You can actually use this equation to figure out what is the wavelength of those particular radio waves. So this radio part of the spectrum, the wavelengths, these are the largest wavelength part of the spectrum. Frequency, this is the lowest frequency part of the spectrum. And the energy per photon is the lowest of this set that we've talked about. Very low energy per photon. Low enough that these radio waves can't cause the biological damage, can't do things like break apart your DNA and do those kinds of things that increase the risk of cancer. Your cell phones, the frequencies that they're using, the frequencies of the electromagnetic radiation that they're using are not high enough to cause cancer. But this is produced by lots of different kinds of systems naturally. Radio waves can be given off by stars, planets, gas clouds, even the afterglow of the Big Bang, the leftover radiation from that early period of expansion in the universe. We can see that afterglow of the Big Bang in this radio part of the spectrum. Again, we'll go into a lot of detail on that much later in the course when we actually get to talking about the universe on larger and larger scales. Again, the point that I really want to make with this is these different kinds of light, these different parts of the electromagnetic spectrum, they're all produced by different kinds of systems, and they all contain different kinds of information. So if we can study the universe in as many parts of the spectrum as possible, we get the greatest amount of data and our best ability to be able to make models of nature around us that explain some of the properties of these celestial objects.